Imagine a library built at the end of science. Inside it rests the final account of nature. One framework joining gravity to quantum physics. One explanation for dark matter. One history of the cosmos, from its earliest measurable moment to its distant future. Every particle is named. Every force is connected. Every mystery that once filled observatories and laboratories has been reduced to a set of principles precise enough to fit inside a single book. Would the universe then be completely understood? At first, the answer seems obvious. Science has always advanced by turning confusion into order. The wandering lights in the night sky became planets moving under gravity. Lightning became electricity. The warmth of a flame became the motion of atoms. Space and time, once treated as an unchanging stage, became parts of a flexible geometry. Again and again, nature surrendered patterns that had been hidden beneath ordinary experience. Why should that process not continue until nothing important remains unexplained? But the book in our imagined library has a strange problem. It is not outside the universe. It is an object within it, made of matter, occupying a place and existing at a particular time. Its readers are also physical beings. Their memories have limits. Their instruments can receive only signals that reach them. Their computers consume energy and require time. And if the book truly describes everything, it must somehow describe itself, its readers, and every consequence produced when its contents are read. The question therefore changes. We are no longer asking only whether nature follows rules. We are asking whether something inside nature can possess a complete account of the whole system that contains it. That word complete hides several ambitions. It might mean discovering the deepest laws from which physical events arise. It might mean knowing every fact about every region of space. It might mean reconstructing everything that has happened, including events whose traces have disappeared. It might mean predicting every future outcome with perfect accuracy. Or it might demand an explanation not only of how the laws work, but why these laws exist instead of others. These goals are often blended together, yet they are not equivalent. A person can understand the rules of chess without knowing every game that will ever be played. A meteorologist can understand the equations governing the atmosphere without predicting the exact position of every cloud months from now. A physicist might discover a unified rulebook for particles and forces without learning the complete history of every particle in the cosmos. Some gaps in knowledge are temporary. A telescope may be too small, a detector too noisy, or a calculation too difficult for present technology. Given better instruments and more powerful computers, such barriers may fall. Other limits may be different. Information may never be able to reach us. Evidence of the past may have been erased. Nature may provide probabilities rather than single predetermined outcomes. A mathematical question may resist every general algorithm. A predictor may fail because its own prediction becomes part of the event it is trying to predict. The difference matters. Saying that humanity does not yet know something is a statement about our present condition. Saying that no observer could ever know it is a claim about the structure of reality itself. The first invites better science. The second demands proof. So this investigation will begin with the strongest possible version of the dream. We will imagine perfect instruments, flawless reasoning, and technologies far beyond anything humans possess. Then, one by one, we will test what complete understanding would require. We will travel outward to the horizon of the observable universe, backward toward the hidden conditions of cosmic history, downward into quantum measurement, and inward toward the logical limits faced by any observer embedded in the world it studies. The purpose is not to declare the universe unknowable. Science has already achieved forms of understanding that would have seemed impossible to earlier civilizations. Nor is the purpose to protect mystery by placing it beyond investigation. A genuine limit must be earned through evidence or reasoning, not announced because a question feels profound. At the end, the final book may still exist, but its meaning may be narrower and more powerful than we first imagined. It may contain the fundamental grammar of reality without containing every sentence the universe will ever write. Before we can ask whether such a book can be completed, we must first decide what knowledge it would actually need to hold. To decide what the final book must contain, we need to separate several kinds of knowledge that ordinary language folds into one word. When we say we understand a falling stone, a living cell, or the expansion of space, we may be claiming very different achievements. The first level is description. A complete description would identify everything that exists and state its condition. For the universe, this would be an inventory beyond imagination. Every field, particle, galaxy, black hole, and region of space, recorded with whatever precision nature allows. Yet description alone is not explanation. An astronomer could chart the position of every visible planet without knowing why planets follow curved paths. A catalog tells us what is there. A law tells us how states are related and how they change. This gives us a second level, knowledge of fundamental laws. Here the goal is not to record every event, but to discover the smallest reliable rulebook capable of describing the basic interactions of nature. This is the ambition usually hidden inside the phrase, theory of everything. The name sounds absolute, but physicists normally use it in a narrower sense. Such a theory would unite the fundamental forces within one consistent framework, including gravity, which is not yet fully reconciled with quantum physics. It would aim to tell us which basic entities and states are possible, and how they can evolve. It would not necessarily tell us where every particle is, which galaxies formed, or what any person will choose tomorrow. The distinction resembles chess. The rules fit into a small booklet. From them arises an enormous landscape of legal games. Possessing the booklet does not reveal every move that has been played, calculate every game that could be played, or explain the strategy of a particular champion. Physics adds another requirement: initial conditions. A law of motion tells us how a state changes. To apply it, we also need a starting state. If two universes obeyed identical laws, but began with different arrangements of matter and energy, their later histories could be very different. A final rulebook might therefore leave a fundamental question untouched. Why did our universe begin in the particular state from which stars, planets, chemistry, and observers could emerge? A third level is predictive completeness. This would mean using laws and conditions to calculate every outcome. Prediction requires more than a correct theory. It requires adequate information about the present and enough resources to carry the calculation through. A short equation may generate behavior so complex that no practical computer can follow every consequence. Later, we will see that some limitations go beyond practical difficulty. But even now, the lesson is clear. Knowing the rule does not guarantee the ability to solve every case. A fourth level is historical completeness. Prediction runs forward. Reconstruction runs backward. To know the entire past, we would need surviving evidence that uniquely identifies what happened. but different histories can sometimes produce the same present appearance. Records can be destroyed, mixed, radiated away, or carried beyond reach. Even perfectly understanding the laws would not automatically restore information that no longer remains available to an observer. Then comes explanatory completeness, the most demanding and least easily measured level. A theory may tell us how a process occurs, while leaving us asking why its laws have that form. Why do these particles exist? Why these constants? Why is there a law-like order at all? Some why questions can be converted into deeper mechanisms. The behavior of gases, for example, becomes intelligible through the statistical motion of molecules. But every deeper account may reveal another level at which assumptions must be accepted rather than derived. There is also understanding across scales. Suppose the final theory describes every fundamental interaction. Would it replace chemistry, biology, psychology, or history? In principle, every cell is made of particles. In practice, the useful explanation of a heartbeat is not a list of quantum states. Higher-level patterns have their own stable relationships. Temperature is meaningful even though no single molecule possesses a temperature. Natural selection explains biological change without tracing every atomic collision inside every organism. Physicists call such descriptions effective theories. They work within particular domains, ignoring details that do not matter at that scale. Effective does not mean false or temporary. It means matched to the level of the question. This creates a challenge for the dream of one final explanation. Reality may possess fundamental laws while still requiring many layers of understanding. Deriving every higher-level fact from microscopic equations could be impossible in practice, unnecessary in method, or in some cases blocked in principle. Completeness at the bottom would not automatically become completeness everywhere above it. The final level is self-completeness. If our imagined book describes the entire universe, it must include the physical process by which the book was written. It must include the brains that understand it, the machines that store it, and the changes caused by anyone reading its predictions. A model that leaves out its observer may be useful, but it is not literally a complete model of everything. We can now state the test more precisely. Complete understanding could mean a full inventory, final laws, exact initial conditions, perfect prediction, total historical recovery, explanations at every scale, and a model that includes itself. These demands may fail for different reasons. Proving that one is impossible does not settle all the others. Achieving one does not guarantee the rest. The old clockwork dream joined them together. It assumed that exact laws and exact knowledge of one moment would unlock every other moment. To discover whether that confidence was justified, we must return to the time when prediction first began to look unlimited. For most of human history, the sky offered patterns without revealing their machinery. The sun rose and fell. The moon changed shape. Planets wandered against the stars, sometimes slowing, stopping, and reversing direction. These motions could be recorded and predicted with growing accuracy, yet the heavens still seemed governed by principles different from those operating on Earth. Then, in the 17th century, that division began to collapse. Isaac Newton showed that the force drawing an apple downward could also hold the moon in orbit. The same mathematical laws connected falling bodies, tides, cannonballs, planets, and comets. Nature no longer looked like a collection of separate stories. It began to resemble one system whose future could be calculated from its present state. The success was profound. Astronomers could use equations to predict where a planet would appear years later. When the orbit of Uranus departed slightly from expectation, mathematicians proposed that an unseen planet was pulling on it. Neptune was then observed near the predicted location. A world had been discovered not by traveling to it, but by trusting that the rulebook remained valid beyond what eyes could see. Achievements like this encouraged a powerful idea. If every physical event has a sufficient cause, and if the laws connecting causes to effects are exact, then uncertainty may belong only to the observer. The future itself could already be fixed, even when human beings lacked enough information to calculate it. Pierre-Simon Laplace gave this confidence its most famous form. He imagined an intellect that, at one instant, knew every force acting in nature and the position and motion of everything that existed. If this intellect were also powerful enough to analyze all that information, then nothing would be uncertain. It would hold the movements of the largest galaxies and the smallest particles within the same calculation. The future would stand before it as clearly as the past. This imagined intellect later became known as Laplace's demon. It was not a supernatural creature introduced to explain nature. It was an ideal test of scientific determinism. Laplace was asking what the classical laws implied if knowledge and calculation were perfect. Human ignorance might be enormous, but ignorance would not be fundamental. Behind our incomplete forecasts, reality would continue like flawless clockwork. The idea contains several assumptions that are easy to miss. First, the universe must have an exact state at every moment. Second, the laws must determine one future from that state. Third, the state must be measurable with unlimited precision. Fourth, the calculation must be possible, no matter how large. Fifth, the intellect must remain unaffected by the system it observes, or somehow include its own effects without contradiction. Classical mechanics made the first two assumptions appear natural. If the position and velocity of an object were known, Newton's equations could determine its motion. Reversing the calculation could also recover where it had been. In this picture, time did not create genuinely new possibilities. It merely revealed a future already contained in the present. But determinism and predictability are not identical. Determinism concerns the relationship between physical states, whether one state leads to a unique later state. Predictability concerns what an observer can learn and calculate. A system may obey exact deterministic laws while remaining unpredictable to anyone who lacks precise data, sufficient time, or adequate computing power. Consider a sealed box containing trillions of colliding molecules. Classical mechanics assigns each molecule a trajectory. Yet following all those trajectories is unnecessary when we want to know the pressure of the gas. Statistical mechanics, instead, connects enormous collections of microscopic motions to stable quantities such as temperature and pressure. The result is reliable understanding achieved without a complete inventory. This was an early warning that the shortest route from fundamental law to useful knowledge might not pass through every microscopic detail. Still, it did not threaten the demon. An unlimited intellect could supposedly perform calculations that humans avoided. Practical difficulty was not a fundamental barrier. To make the demon truly complete, however, its knowledge would need to be extraordinary. It could tolerate no missing region. A single, unmeasured influence might alter later events. It could tolerate no uncertainty in the initial state, because an error in the beginning could infect the result. It would need unlimited memory to store the state of the universe and unlimited speed to calculate its development before the predicted events occurred. There is also a deeper cost. The demon cannot stand on an imaginary platform outside reality. If it exists, it must have a physical body or mechanism. Gathering information requires signals. Storing information requires distinguishable physical states. Calculation requires processes that unfold in time and consume resources. The demon must therefore obey the same laws it hopes to master. This creates a tension already visible before quantum mechanics or modern cosmology enters the story. To predict the entire universe, the intellect needs a model containing every relevant detail. But that model must include the intellect itself, including the state of its memory and the prediction it is about to announce. If an event changes after the prediction is revealed, the calculation must include that response as well. For the moment, we can set this self-reference aside. Give the demon impossible memory and perfect reasoning. Allow it to measure without disturbing anything. Assume the universe is deterministic. Even under these generous conditions, one requirement remains unavoidable. Information must reach the predictor. Newtonian physics quietly imagined a cosmos in which influences could be treated as immediately available. Modern relativity removed that convenience. No signal travels faster than light, and the universe has a finite age. An observer can receive evidence only from regions whose light has had time to arrive. The clockwork dream therefore faces its first physical test before any calculation begins. The demon may understand every law and make no mathematical mistake. No intelligence can calculate missing information. But if part of the cosmic state lies beyond all possible contact, its perfect equation starts with an incomplete page. Every act of observation begins with a messenger. Light enters a telescope. A radio wave reaches an antenna. A particle strikes a detector. Even when an object is far too distant to touch, some physical influence must travel from it to us. Without that connection, the object may exist, but it cannot become part of our direct evidence. The speed of that connection is limited. Light travels through empty space at roughly 300,000 kilometers per second, an extraordinary speed that is still finite. Sunlight takes about 8 minutes to reach Earth. We therefore see the sun not as it is at this instant, but as it was 8 minutes earlier. Light from the nearest star beyond the sun takes more than 4 years. Light from a galaxy millions of light-years away began its journey before modern humans existed. A telescope is therefore a machine for looking into the past. The farther it reaches, the earlier the image it receives. This makes astronomy possible, but it also creates a boundary. The universe has a finite age, so light has had only a finite time to travel. There are regions from which no signal has yet reached us, and perhaps regions from which no signal ever will. The boundary of what we can currently observe is not a wall at the edge of space. If an astronomer somehow traveled toward it, the boundary would move with the astronomer, because every observer has a horizon centered on their own history. The observable universe is simply the region connected to us by signals since the early cosmos became capable of sending the evidence we can now detect. This leads to a number that initially appears impossible. The universe is about 13.8 billion years old, yet the present distance to the most remote matter, whose ancient light we receive, is roughly 46 billion light-years. Nothing had to travel faster than light to produce this result. While the radiation crossed the cosmos, space itself expanded. The matter that emitted the ancient signal is now much farther away than the distance light could travel through an unchanging universe during the same period. Cosmologists call the relevant boundary the particle horizon. The word horizon is useful because it resembles the horizon on Earth. It marks the limit of what is visible from a position, not necessarily the end of the world. Beyond our cosmic horizon may lie more galaxies, more matter, and more space. Current observations do not reveal how far the full universe continues. Measurements of the cosmic microwave background provide the most precise large-scale picture available. This radiation was released when the early universe cooled enough for light to travel freely, around 380,000 years after the hot Big Bang phase began. Missions including Planck mapped tiny temperature variations across that ancient glow. From those patterns, scientists infer the contents, geometry, expansion history, and approximate age of the observable cosmos. Planck's results fit remarkably well with the standard 6-parameter cosmological model, usually called lambda-CDM. Within that framework, space is consistent with being very close to geometrically flat on large scales. But flatness does not tell us whether the entire universe is finite or infinite. A flat surface can continue without end, or it can possess a connected topology that makes its total extent finite. The measurements constrain possibilities. They do not provide a view from outside the whole. The distinction between the observable universe and the entire universe is essential. Popular images often show a glowing sphere and label it the universe, as though everything ends at its surface. What the sphere actually represents is our accessible region. Another observer in a distant galaxy would have a different observable sphere, overlapping ours but centered elsewhere. Neither viewpoint would be privileged. Expansion creates a second kind of boundary. The expansion of the universe is accelerating, which means some sufficiently distant regions recede from us in such a way that signals emitted there now will never reach Earth, even given unlimited waiting time. This boundary is called a cosmic event horizon. The particle horizon concerns what has been able to influence us so far. The event horizon concerns what will ever be able to influence us in the future. No improvement in telescope design can defeat a causal horizon. A larger mirror can collect fainter light that arrives. A more sensitive detector can reveal signals hidden in noise. Neither can capture a message that has not reached us, or one that never can. The limitation belongs not to the instrument, but to the structure of space-time connecting observer and event. Does this mean everything beyond the horizon is scientifically meaningless? No. Scientists can infer properties of unseen regions by testing whether the laws measured here remain consistent across the accessible cosmos. A successful model may imply that space continues beyond our view. Patterns within our horizon can also constrain the geometry and early history of a much larger domain. But inference must not be confused with possession of every fact. The same observations may remain compatible with more than one global size, topology, or distant arrangement. If no signal from a region can reach us, we cannot inspect each object there or confirm every event that occurs. A theory can describe possibilities beyond the horizon without turning inaccessible details into observed knowledge. This is the first serious failure of Laplace's requirement. The demon demanded the exact state of everything at one moment. Relativity and cosmology divide reality into regions connected and disconnected by causal structure. Even a flawless observer cannot receive an instantaneous report from the whole cosmos, because there is no universal present across which such reports could be gathered, and signals require time. Yet the dream has one possible defense. Perhaps the demon does not need to observe every region directly. If the laws are known, it might reconstruct hidden states from the traces that remain inside our horizon. Cosmology already recovers astonishing information from ancient light. The microwave background, elemental abundances, galaxy distributions, and gravitational waves all preserve fragments of earlier conditions. That crucial distinction will now become decisive. The next question is therefore more subtle than distance. When the universe changes, does it retain enough evidence for its entire history to be recovered? Or can different beginnings leave behind the same observable world? The past does not arrive as a complete recording. It survives in fragments. A photon carries evidence of the object that emitted it. An element inside a star carries evidence of earlier nuclear reactions. A fossil preserves the shape of an organism while losing almost everything about its individual life. To reconstruct history, science reads the marks that earlier events leave on the present. Cosmology performs this reconstruction on the largest possible scale. The expansion of space, the abundance of light elements, the distribution of galaxies, and the cosmic microwave background all point toward a hotter, denser early universe. None is a photograph of the absolute beginning. Together, however, they form a consistent history reaching far beyond any written memory. The cosmic microwave background is the most ancient light we can observe directly. During the first hundreds of thousands of years, matter existed as a hot plasma of charged particles, photons, repeatedly scattered from free electrons, and could not travel far. As expansion cooled the plasma, electrons joined atomic nuclei. Light then moved much more freely, carrying a pattern from roughly 380,000 years after the hot Big Bang phase began. That pattern is remarkably smooth, but not perfectly smooth. Tiny temperature differences reveal small variations in density. Over billions of years, gravity amplified those variations into stars, galaxies, and the cosmic web. By studying the size and arrangement of these fluctuations, cosmologists test models of the universe's contents and early development. The smoothness also creates a puzzle. Widely separated regions of the microwave sky have nearly the same temperature. In a simple expanding model, without an earlier special phase, some of those regions appear too far apart ever to have exchanged enough light or heat to reach such similar conditions. Why should disconnected parts of the early cosmos look so alike? Cosmic inflation was developed partly to address this horizon problem. In broad terms, inflation proposes that an extremely early region underwent a brief period of accelerated expansion. Areas that were once close enough to interact could have been stretched across distances that later became enormous. Their shared earlier conditions would then help explain the large-scale uniformity we observe. Inflation offers another powerful idea. Quantum fluctuations present during that early phase could have been stretched to cosmic scales. These slight variations would later become the seeds from which galaxies grew. Observations show a primordial pattern that is nearly scale-invariant and predominantly adiabatic, features compatible with broad inflationary predictions. Compatible does not mean uniquely proven. Many different inflationary models can produce similar observable patterns, and important details remain unsettled. Scientists do not yet know the exact field or mechanism that would have driven inflation. Alternatives and modifications continue to be investigated. The evidence supports a successful framework, but it does not provide a single, complete movie of the earliest moment. This uncertainty reveals a general problem in historical reconstruction. Different causes can leave similar surviving effects. If several early scenarios produce nearly the same microwave pattern, later measurements may narrow the possibilities without selecting one unique past. Better instruments can recover fainter traces, but they cannot guarantee that every distinction between possible histories still exists in accessible evidence. Inflation may itself make the problem sharper. Rapid expansion can dilute particles, curvature, and other features inherited from an earlier phase. This helps explain why the later universe appears smooth and geometrically simple. But it also means that traces of whatever preceded inflation may have been stretched or weakened beyond recovery. The process that explains the observable order may hide part of the history that came before it. It would be too strong to say, inflation erased every earlier fact. The answer depends on the model, its duration, and the physics operating at energies we cannot currently test directly. Some pre-inflationary signatures might survive in unusual correlations, gravitational waves, or other subtle features. Searches for such evidence remain scientifically valuable precisely because complete erasure has not been established. Even within the observable sky, a limit called cosmic variance appears. Scientists usually learn statistical patterns by examining many independent examples. For the largest structures in cosmology, however, we possess only one observable universe. We cannot rerun cosmic history with different initial conditions, or observe thousands of independent skies from outside. At the broadest scales, the number of available samples is limited by the cosmos itself. Cosmic variance is not ordinary measurement noise. A perfect instrument could map our microwave sky without error and still confront uncertainty about the statistical process that generated it. We see one realization of that process. The largest patterns contain only a small number of independent modes, so some uncertainty cannot be reduced simply by building a better detector. There are other ways information can become inaccessible. Light may cross an event horizon. Radiation can scatter until its original source is difficult to reconstruct. Complex interactions can spread a local record across countless degrees of freedom. Black holes create an especially deep version of the question, although the relation between their information and quantum gravity remains an active field rather than a settled shortcut to the conclusion. This does not make cosmology guesswork. Scientific reconstruction does not require an untouched archive. It compares models, searches for independent traces, makes quantitative predictions, and rejects histories inconsistent with observation. The success is extraordinary. From faint radiation and elemental ratios, humans have inferred conditions billions of years before Earth existed. But success within surviving evidence differs from recovery of every event. Imagine several messages pass through a machine that removes most letters and preserves only the same short fragment. Understanding the machine may tell us why the fragment survived. It may let us identify broad features shared by the original messages. It cannot reveal distinctions that the process no longer records. The same caution applies when equations are reversible. A microscopic law may allow states to evolve backward mathematically, yet reconstruction still requires the exact later state. An observer who lacks inaccessible correlations cannot simply command the equations to restore them. Reversibility in a law is not the same as recoverability for a physical investigator. The surviving cosmos is therefore both an archive and a filter, preserving enough to reveal history while withholding distinctions that no later measurement can restore. Laplace's demon therefore faces a second missing page. The first was written beyond our causal horizon. The second may have been blurred by cosmic evolution itself. A sufficiently successful theory can constrain invisible history, sometimes with astonishing precision, but it cannot manufacture evidence absent from the state available to the observer. Still, the demon might retreat to a narrower claim. It may concede that the full past cannot be recovered, while insisting that, given the best possible present state, the future remains exactly determined. That defense now encounters a change more radical than distance or damaged records. At the quantum level, nature does not always offer predictions in the classical form Laplace imagined. Classical uncertainty usually suggests missing information. A tossed coin appears unpredictable because we do not know its exact motion, the air currents around it, or the surface on which it will land. In principle, Laplace's demon could include those details and calculate whether the coin will show heads or tails. Quantum experiments introduced a different kind of prediction. Imagine sending individual particles toward a detector through an apparatus with two possible paths. Each particle arrives at one definite point, yet repeated trials gradually build an interference pattern, the kind of pattern normally associated with waves. If the experiment is changed to reveal which path each particle takes, the observed pattern changes. The arrangement used to ask the question becomes part of the physical situation. Quantum theory represents a system with a quantum state. From that state, physicists calculate probabilities for possible measurement outcomes. The theory does not merely say that our instruments are poor, it predicts the statistical pattern with extraordinary precision, while, in its standard operational use, assigning probabilities to individual results. This distinction matters. Suppose a particular measurement has two possible outcomes. Quantum theory may predict that one will appear 60% of the time and the other 40%. After many trials, the frequencies can approach those values with remarkable accuracy. But the theory does not generally supply a hidden schedule saying which outcome must occur on each specific trial. The uncertainty principle sharpens the break from classical intuition. Certain pairs of physical quantities, such as position and momentum, cannot both be assigned arbitrarily sharp quantum values in the same state. This is not simply the claim that measuring one carelessly disturbs the other. The limitation is built into the mathematical structure connecting the quantities and the states used to describe them. An everyday measurement error can, at least in principle, be reduced by improving the instrument. Quantum uncertainty is different. Preparing a state with a narrower range of positions necessarily produces a broader range of momenta according to the uncertainty relation. The theory changes what counts as a complete physical specification, not merely how accurately a technician reads a dial. Does this destroy determinism? The answer depends on what is meant and on how quantum theory is interpreted. The quantum state evolves according to a precise equation between measurements. The controversy begins when that state is connected to a particular observed outcome. Different interpretations describe this connection in different ways. Some interpretations treat individual outcomes as fundamentally probabilistic. Others preserve deterministic evolution by proposing branching worlds, hidden variables, or additional structure. These accounts can agree on the predictions of many experiments, while disagreeing about what reality is doing when no measurement result has been recorded. The experimental success of quantum mechanics is not the same as agreement about its ontology. Bell's theorem and the experiments inspired by it place powerful restrictions on possible explanations. Measurements performed on entangled systems show correlations that cannot be reproduced by theories satisfying the relevant form of local hidden variables. These results close an important classical escape route. They do not prove that human consciousness creates reality, that nothing exists before observation, or that every conceivable deeper description is impossible. For the question of complete understanding, the careful conclusion is stronger than a slogan and narrower than a philosophical verdict. Standard quantum theory may provide the fullest possible prediction as a probability distribution rather than a single guaranteed outcome. A law can be exact even when the event it predicts is not individually certain within that framework. The result is not a failure of precision, but a new kind of precision. Classical physics tries to assign one path and one later state. Quantum physics assigns amplitudes whose combinations determine observable probabilities. What remains uncertain in an individual trial can therefore coexist with predictions so accurate that experiments test them to decimal places. The rulebook becomes probabilistic without becoming vague. This changes the ideal of knowledge. Laplace imagined uncertainty shrinking towards zero as information improved. Quantum physics suggests that some uncertainty cannot be removed by simply measuring more carefully. The best prediction available may contain irreducible alternatives, with precisely defined probabilities. Yet probability is not ignorance in the ordinary sense. Quantum theory predicts atomic spectra, semiconductor behavior, lasers, and countless experimental results with exceptional accuracy. It may tell us less than Laplace demanded about one future event, while telling us exactly how collections of events will be distributed. Scientific understanding survives, but its form changes. There is also a limit on copying information. An unknown quantum state cannot generally be duplicated perfectly through a universal process. This no-cloning principle follows from quantum mechanics and matters for any imagined archive attempting to collect flawless copies of every state. Quantum information can be transferred and protected in special ways, but it cannot be treated like unlimited classical text, copied without restriction. Measurement creates further practical and conceptual difficulties. To learn about a system, an apparatus must interact with it. The apparatus then becomes correlated with what it measures. In ordinary large objects, environmental interactions rapidly suppress visible quantum interference through decoherence. This helps explain why the world appears classical at familiar scales, although decoherence alone does not settle every interpretive question about definite outcomes. Our imagined demon can no longer be granted the innocent role of a spectator reading a fully exposed classical state. It is a physical participant. The questions it asks determine which experimental arrangements are built. The information it can extract is constrained by the quantum structure of the systems and measurements involved. Still, quantum mechanics should not be used as a shortcut to declare the universe incomprehensible. Probability distributions are understandable. Quantum states are mathematically tractable. Experiments can distinguish successful predictions from failed ones. A universe without predetermined classical outcomes may remain lawful, testable, and deeply intelligible. The damage to complete prediction is specific. If individual outcomes are genuinely probabilistic, no amount of prior data lets an observer announce every future event with certainty. If a deterministic interpretation is correct, the observer may still lack access to the hidden information or branches required for such a forecast. Either way, the classical promise that an exact present delivers one knowable future is no longer straightforward. One defense remains. Perhaps quantum probabilities are the only unavoidable uncertainty. For everything larger, a sufficiently powerful computer might still calculate all meaningful developments from the best allowed state. But even systems governed by deterministic equations can defeat long-range prediction when tiny uncertainties grow. The next limit does not begin with quantum mystery. It begins with ordinary motion, repeated until a small difference becomes another world. A pendulum seems simple. Give it a gentle push, and its motion can be calculated with familiar equations. Join several pendulums together, however, and the movement can become wildly sensitive. Two arrangements that begin almost identically may remain close for a while, then separate until their later motions appear unrelated. Nothing random has been added. The equations are still deterministic. What has changed is the value of precision. This is the territory of chaos. In a chaotic system, small differences in initial conditions can grow rapidly. The popular phrase, butterfly effect, captures the image but often loses the science. A butterfly does not control every storm, and tiny changes do not become enormous in every system. The point is that particular nonlinear systems repeatedly stretch differences, making long-range forecasts increasingly dependent on details that were initially too small to measure. Weather provides the clearest example. The atmosphere follows physical laws involving temperature, pressure, moisture, radiation, and fluid motion. Forecasting begins by measuring its present condition, then using equations to project that condition forward. But measurements never contain infinitely many digits. Stations are separated by distance. Satellites have finite resolution. Every instrument includes some uncertainty. For a short forecast, those uncertainties may remain manageable. As the simulated atmosphere evolves, however, small differences between possible starting states grow. After enough time, forecasts that began almost together can describe very different weather. Better observations and models extend useful prediction, but chaos prevents unlimited improvement from producing an infinitely distant exact forecast. This is called a predictability horizon. It is not a physical wall like the cosmic horizon. Information from tomorrow's atmosphere is not forbidden from reaching us once tomorrow arrives. The limit concerns how far a present state can support a detailed forecast before amplified uncertainty overwhelms it. Chaos must also be distinguished from quantum probability. A classical chaotic model can be completely deterministic. One exact state leads to one exact future. Its unpredictability arises because an observer cannot specify the initial state with infinite precision and cannot calculate with infinite accuracy. Quantum mechanics adds deeper restrictions on which quantities can be sharply specified together. In real physical systems, the two kinds of limitation can interact without becoming the same thing. Laplace's demon might object that finite precision is merely a human weakness. Give it perfect measurements, and chaos would no longer matter. But a physical demon cannot store an infinite string of digits in a finite memory. Any device representing a continuous quantity must use distinguishable physical states. If the accessible matter and energy are finite, so is the information the device can reliably encode. Even an exact symbolic description does not guarantee an easy calculation. Some problems require resources that grow explosively as the system becomes larger. A computer may understand the rule for checking a proposed solution while being unable to search the enormous space of possibilities within any useful time. This is computational complexity, the study of how the time and memory required for solving problems scale with their size. The difference between a short law and a difficult consequence appears throughout science. The equations governing interacting particles can be compact, yet solving them exactly for large collections becomes unmanageable. Gravitational systems, turbulent fluids, protein folding, and quantum many-body behavior can produce vast spaces of possible configurations. Approximation, simulation, statistics, and effective theories become essential not because the laws are abandoned, but because direct derivation is too costly. Imagine a computer built from every usable particle in the observable universe. It still could not perform an unlimited number of operations in a finite time. It would have bounded memory, bounded energy, and bounded communication speed. Enlarging the computer also creates delays, because information cannot move instantaneously between its parts. Unlimited calculation is not an engineering destination. It is an assumption that removes the calculator from physics. There may also be processes for which prediction offers no substantial shortcut over evolution itself. To learn the state after a billion steps, a simulator may need to reproduce something close to those billion steps. The rule can be simple, while its unfolding contains patterns that cannot be compressed into a much faster general calculation. This idea, often discussed as computational irreducibility, must be used carefully, because proving it for a particular physical system can be difficult. Still, it exposes a crucial possibility. Knowing the program is not the same as possessing its output in advance. A familiar comparison is a novel generated by a short set of grammatical rules. The rules constrain every valid sentence, but they do not contain a readable summary of every story that can be written. Likewise, physical laws may define the space of possible developments without providing an instant lookup table for all their consequences. Science responds to these limits by changing the level of the question. Meteorology predicts ranges and probabilities rather than the path of every air molecule. Thermodynamics predicts pressure and entropy while ignoring microscopic trajectories. Population biology tracks distributions and selection pressures instead of every molecular collision. These descriptions are not admissions of defeat. They identify stable patterns that remain predictable when fine details are unavailable. This explains why understanding can increase even when exact prediction does not. Recognizing a system as chaotic tells us why forecasts lose precision and how quickly that loss occurs. Complexity theory identifies classes of problems and estimates the resources they demand. Statistical mechanics discovers reliable collective laws. The boundary becomes part of the explanation. But the clockwork promise has weakened again. Deterministic evolution no longer guarantees that an observer inside the universe can obtain or process the information required for complete prediction. A vanishingly small uncertainty may eventually correspond to a visibly different world. A compact equation may demand more calculation than the cosmos can physically perform. It is tempting to conclude that the search for fundamental laws has therefore failed. That would be a mistake. Chaos and complexity concern the consequences of laws, not necessarily the possibility of discovering the laws themselves. A final framework might still exist, even if no computer can derive every event from it. This distinction preserves the deepest version of the scientific dream. Perhaps the universe cannot be replayed in advance, but its basic grammar could still be written down. Perhaps the final book was never meant to contain the weather on every planet or the motion of every atom. Perhaps it only needs the rules from which all such behavior arises. The dream does not disappear here. It contracts from total foresight into a search for fundamental principles, leaving consequences to emerge through processes that may resist compression. At the midpoint of our investigation, that possibility forces a reversal. We began by treating a theory of everything as a complete account of everything that happens. Physics uses the phrase more carefully. The final theory, if it exists, may be complete as a foundation, while remaining radically incomplete as a prediction, history, or explanation of every higher-level fact. The next step is therefore not another obstacle to calculation. It is a correction to the question itself. Before asking whether the final rulebook can be found, we must understand why possessing that rulebook would not place the whole universe inside our hands. The phrase, theory of everything, invites an image of total possession. It sounds like an equation that answers every question, explains every event, and turns the universe into a solved puzzle. But this image asks fundamental physics to deliver something its actual goal does not promise. Modern physics already contains a remarkably successful rulebook called the Standard Model. It describes the known elementary particles and three fundamental interactions: electromagnetism, the strong nuclear force, and the weak nuclear force. Its predictions have survived demanding experiments, sometimes matching measurements to astonishing precision. Yet the Standard Model does not include a quantum theory of gravity, and it leaves major questions open, including the nature of dark matter and the origin of several measured parameters. General relativity provides our best description of gravity on large scales. It treats gravity not as an ordinary force moving through a fixed arena, but as the geometry of space-time, responding to matter and energy. The theory explains planetary motion, gravitational lensing, black holes, the expansion of the universe, and gravitational waves. But when quantum effects and strong gravity must be handled together, the two frameworks do not yet form one complete tested description. A theory of everything would normally mean a framework that resolves this division and describes all fundamental interactions consistently. It might identify deeper entities from which particles and space-time emerge. It might explain relationships among constants that currently appear independent. It might show why the Standard Model and general relativity work so well within their domains. That would be one of the greatest achievements in intellectual history. It would not, however, contain the exact arrangement of every object. Laws specify possibilities and transformations. They do not automatically specify which allowed state the universe occupies. The rulebook still needs boundary conditions, initial conditions, or some deeper principle that selects them. Even with those conditions, deriving every later fact would remain another task. Consider water. In principle, the behavior of its molecules is grounded in quantum physics. Yet the useful concepts for describing a wave include pressure, viscosity, turbulence, and temperature. These are collective properties. No isolated molecule is wet, and no single molecule has the temperature assigned to a glass of water. The properties emerge from relationships among enormous numbers of components. Emergence does not require a mysterious substance added to physics. It means that organized systems display stable patterns, best described at a level different from their microscopic ingredients. A traffic jam moves backward along a road, even though every car moves forward. The backward-moving jam is real and measurable, but it is not an extra vehicle. It is a pattern created by interactions among vehicles. The same layered structure appears throughout nature. Quantum interactions support atoms. Atoms form molecules. Molecules participate in cells. Cells organize into organisms. Organisms build ecosystems and societies. Each level remains physically connected to the levels below. Yet the questions asked at one level may require concepts absent from another. Knowing particle physics does not replace evolutionary theory when explaining why a population changes across generations. Calculating atomic motions does not by itself identify a predator-prey relationship. A complete microscopic description of a brain, even if obtainable, would not automatically provide the clearest explanation of a memory, decision, or language. Higher-level explanations track regularities that disappear when attention is restricted to individual particles. Physicists manage this layered reality using effective theories. An effective theory describes the variables and laws that matter within a particular range of scales. Fluid mechanics ignores most molecular details while predicting currents and waves. Thermodynamics relates heat, work, temperature, and entropy without calculating every collision. These theories are not merely placeholders waiting to be discarded. They can remain valid and indispensable even when deeper microscopic laws are known. This is possible because many microscopic arrangements can produce the same large-scale behavior. A gas can have the same temperature and pressure, while its molecules occupy countless different, detailed states. If the higher-level outcome does not depend on most microscopic differences, an explanation that tracks all those differences adds calculation without adding understanding. The meaning of reduction must therefore be handled carefully. A higher-level process may depend entirely on physical ingredients without being usefully predicted from the bottom upward. Saying that biology is compatible with physics is not the same as saying a particle equation replaces biology. The foundation constrains the structure above it, while new patterns create new explanatory needs. This distinction also changes how progress should be measured. Physics need not predict a storm, organism, or conversation to succeed as fundamental physics. Its task is to reveal the constraints under which such events become possible. Other sciences then discover regularities within those constraints. Understanding grows as a network of compatible explanations, not necessarily as one calculation, descending from a final equation to every detail. This reverses the assumption with which our investigation began. We imagined the final book as an exhaustive cosmic transcript. Fundamental physics seeks something closer to a grammar. A grammar can define what sentences are possible without listing every sentence, identifying every sentence ever spoken, or explaining what each speaker meant. The reversal protects the idea of a final theory from objections that were never aimed at it. Causal horizons may block a complete inventory without blocking universal laws. Chaos may prevent exact long-range forecasts without making the underlying equations false. Quantum probabilities may replace single outcomes, while remaining governed by a precise mathematical framework. Computational limits may obstruct solutions without preventing the rules from being stated. But the reversal also makes the title more demanding. If a final rulebook counts as complete understanding, we must ask what complete means for the rulebook itself. Could one finite formal structure capture every fundamental physical truth? Could it decide every meaningful question that can be asked within its domain? Could it establish its own consistency? Could an observer inside the universe know that no deeper rule remains? These are not questions about building a faster telescope. They concern the relationship between a formal system and the truths expressible within it. Mathematics appears to offer unlimited clarity, because a proof can establish a conclusion with certainty. Yet during the early 20th century, mathematicians discovered that sufficiently powerful formal systems contain limits no increase in patience can remove. The discovery did not show that mathematics was unreliable. It showed that proof has a structure, and that structure can generate statements a chosen rule system cannot settle from within itself. The dream of one perfectly sealed foundation had encountered self-reference. Physics does not inherit this conclusion automatically. The universe is not simply a textbook, and equations are models rather than reality itself. Still, any proposed final theory intended to generate predictions through formal rules must confront the question: if its mathematical language is powerful enough to encode computation and arithmetic, might some consequences resist proof or decision within that framework? We have reached the true midpoint. Complete knowledge of events has already separated from complete knowledge of laws. Now even the completeness of laws must be examined on its own terms. To do that, we must follow a sentence designed to speak about the rulebook containing it, and discover why no sufficiently powerful rulebook can settle every such sentence. At the beginning of the 20th century, mathematics appeared ready for complete organization. Its many branches had grown powerful, but questions about their foundations remained. Could every valid mathematical statement be proved from a clear collection of axioms? Could contradictions be ruled out? Could a mechanical procedure determine whether any proposed statement was true or false? David Hilbert became a leading voice for this ambition. The goal was not to list every theorem in advance. It was to build a secure formal foundation from which mathematical truths could, in principle, be derived. A formal system begins with symbols, starting assumptions called axioms, and precise rules for moving from one statement to another. A proof is then a finite sequence of permitted steps. Three qualities seemed especially desirable. The system should be consistent, meaning it cannot prove both a statement and its negation. It should be complete, meaning every properly stated question within its scope can be settled. And its procedures should be effective, meaning the rules can be followed mechanically, rather than depending on intuition. In 1931, Kurt Gödel showed that these goals cannot all be achieved by every sufficiently powerful formal system. His first incompleteness theorem concerned systems capable of expressing enough arithmetic. If such a system is consistent and effectively axiomatized, there will be statements in its language that it can neither prove nor disprove from its own axioms. The result is often reduced to the phrase, "There are true statements that cannot be proved." That summary points in the right direction but requires care. Truth and probability are not identical. Truth refers to how a statement is interpreted in a mathematical structure. Probability refers to whether the statement follows from a chosen formal rulebook. Gödel exposed a gap between the two. The central mechanism involves self-reference. though not the loose paradox of a sentence simply declaring itself false. Gödel developed a way to encode statements, proofs, and relationships between them using numbers. This allowed arithmetic to express claims about its own process of proof. A carefully constructed statement could, in effect, assert that it has no proof within the system. If a consistent system proved that statement, it would create the very contradiction the statement denies. Yet if the system cannot prove it, the statement correctly describes its own unprovability under the intended interpretation. The formal structure becomes unable to settle a meaningful claim generated through its own expressive power. Gödel's second incompleteness theorem reaches further. Under the relevant conditions, a sufficiently strong, consistent system cannot prove its own consistency using only its internal resources. This does not mean no reasoning about consistency is possible. A stronger system may prove the consistency of a weaker one. But the stronger system then faces questions about its own foundation. Moving upward does not create a final self-certifying platform. One useful way to picture this is to imagine a legal code able to describe not only actions, but also every application of its own rules. Eventually, the code can express cases whose status depends on what the code can establish about itself. Adding a rule may settle one case, but the enlarged code can generate another. The problem is not that the judges need more time. It arises from the combination of consistency, expressive power, and self-reference. Mathematics becomes open-ended. Each extension may reveal truths unavailable to the earlier system, without producing a framework that proves every statement and certifies itself. This open-endedness resembles scientific progress. But resemblance is not identity. Nature must supply the bridge. A related boundary appeared through computation. Alan Turing imagined an abstract machine that follows exact instructions. He then considered the halting problem. Can one general algorithm inspect any possible program and input, and always decide whether that program eventually stops or runs forever? Turing proved that no such universal procedure exists. Many individual programs can be analyzed successfully. Some clearly halt, and others clearly continue. The impossibility concerns a single method guaranteed to decide every possible case. This distinction will matter when physical undecidability enters the story. A general limit does not make all particular questions unsolvable. Gödel and Turing did not show that mathematics had collapsed. Mathematics continued to develop with immense power. Their work clarified the boundaries of formal proof and algorithmic decision. A system can be reliable and extraordinarily productive without being able to settle every statement expressible within it. The temptation is to carry this conclusion directly into physics. If physical theories are written in mathematics, one might say, then Gödel proved that no theory of everything can be complete. But that step is too fast. A theorem about formal axiomatic systems does not automatically become a theorem about nature. The universe is not known to be identical to one effectively axiomatized formal system. A physical theory may aim to describe observations rather than enumerate every arithmetical truth. A law can be complete in the limited sense of covering fundamental interactions, even if the mathematics used to explore its consequences contains undecidable propositions. We must specify what kind of completeness is being claimed and which physical questions the formal limit affects. Stephen Hawking explored this possibility in a 2002 lecture titled Gödel and the End of Physics. Earlier in his career, he had expected the search for fundamental theory eventually to reach a final formulation. He later argued that the relationship between a theory, its models, and observers inside the universe may prevent a finite final account of the sort once imagined. Hawking's change of mind is historically important, but it is not an experimental result or a universally accepted proof. His argument uses Gödel as part of a broader reflection on physics, self-reference, and model building. Other thinkers dispute whether incompleteness blocks a final physical law rather than merely limiting what can be derived within a formal representation. The cautious question is conditional. Suppose a future physical theory is expressed as a consistent, effectively axiomatized system, powerful enough to encode arithmetic or universal computation. Suppose further that physically meaningful questions can be mapped onto statements within that system. In that case, some questions may resist proof or algorithmic decision from within the chosen framework. Even then, several conclusions must remain separate. An undecidable statement within a theory does not necessarily describe an observable experiment. A proposition may be formally independent while having little physical relevance. A larger framework may settle a question left open by a smaller one, although it will acquire limits of its own. And inability to prove a result does not automatically imply that the corresponding physical event cannot occur. These distinctions protect the investigation from turning a precise theorem into a vague declaration that everything is unknowable. Gödel does not license mysticism. He does not show that logic is useless or that every truth is relative. He establishes exact limits for exact kinds of formal systems. Yet the philosophical force remains. A final rulebook powerful enough to describe complex reality may also be powerful enough to formulate questions about its own operations. Completeness and self-certification can then pull against each other. The very expressiveness that makes a theory ambitious may prevent it from closing every loop within itself. So far, however, the barrier remains formal. It lives in axioms, proofs, and abstract machines. To affect our central question decisively, undecidability must connect to a property recognizable as physics, rather than merely to arithmetic written in unusual symbols. That connection emerged from an unexpected place: the energy structure of quantum matter. Researchers asked a question that sounds concrete and physical. Given the local rules governing a quantum system, is there a fixed energy gap above its lowest energy state? For specially constructed families of systems, the answer cannot be determined by any universal algorithm. The sentence "no rulebook can settle" is about to become a material question. To see how undecidability can enter physics, begin with energy. A quantum system has possible energy levels. Its lowest possible energy defines the ground state. Above that ground state may be excited states, reached by supplying energy to the system. The difference between the ground state energy and the next available range of energies is called the spectral gap. The gap matters because it helps determine how matter behaves on large scales. A system with a non-zero gap resists low-energy excitations. A gapless system can respond to arbitrarily small additions of energy in the infinite size limit. This distinction is connected to phases of matter, correlation lengths, and the stability of physical behavior. For a small quantum system, its energy levels can sometimes be calculated directly. But physicists often care about the thermodynamic limit. What happens as the system grows without bound? Given a local rule describing how neighboring components interact, can an algorithm always determine whether the corresponding infinite system is gapped or gapless? The question appears concrete. The input is a mathematical description of local interactions. The requested output is one of two physical classifications. One might expect that enough computation would always produce an answer, even if the calculation became extremely difficult. In 2015, Toby Cubitt, David Perez Garcia, and Michael Wolf showed otherwise for specially constructed families of two-dimensional quantum systems. They proved that the spectral gap problem is undecidable in general. There is no single algorithm that accepts every Hamiltonian in the relevant family and always correctly determines whether the infinite system has a spectral gap. A Hamiltonian is the mathematical object that encodes a system's energy and dynamics. In the construction, local interactions are designed so that the large-scale energy structure depends on the behavior of a computation. The computation can be connected to a halting problem, whether a programmed process eventually stops or continues forever. If a universal method could always decide the spectral gap for these systems, it could also decide the encoded halting problem. Turing's proof shows that no algorithm can do that for every possible program. The physical classification, therefore, inherits the undecidability of the computation embedded within its mathematical structure. The result is startling because the local rules can be stated clearly. Nothing is missing from the definition of the model. The difficulty is not ordinary numerical imprecision or lack of patience. For the family considered, no general algorithm can map every allowed description to the correct gapped or gapless answer. Later work extended spectral gap undecidability to constructed one-dimensional quantum spin chains with translationally invariant nearest neighbor interactions. One dimension often permits methods unavailable in more complicated geometries, so the extension showed that reducing spatial dimension does not automatically restore a universal decision procedure. This is a genuine bridge between abstract computation and a property expressed in physical language. A short set of interaction rules can generate a question whose answer no universal algorithm extracts for every member of the family. Fundamental equations may therefore contain consequences that resist systematic decision. But the bridge has railings, and crossing them carelessly produces false conclusions. The theorem does not say that every quantum material has an unknowable spectral gap. It does not prevent physicists from calculating or measuring gaps for many particular systems. It does not imply that a laboratory can never settle whether a specific sample behaves as gapped or gapless within experimental precision. Undecidability concerns a general procedure guaranteed to work for every valid input in the defined class. Individual cases may be easy, difficult, or solvable through special knowledge. The same is true of the halting problem. Many programs obviously stop, while others obviously repeat forever. What cannot exist is one algorithm that correctly decides all programs. The thermodynamic limit also matters. Real samples contain finitely many components. An experiment measures finite systems for finite durations and with finite precision. The theorem concerns what happens as size becomes unbounded within the mathematical model. Connecting that limit to laboratory reality requires careful interpretation rather than a dramatic leap. The constructed Hamiltonians are legitimate quantum models, but they are deliberately engineered to encode computation. They are not evidence that undecidability dominates ordinary materials. Their importance lies elsewhere. They disprove the assumption that every clearly formulated property of local quantum models must be decidable by one general algorithm. Recent research adds another caution. A 2026 analysis found that the undecidable behavior in a particular one-dimensional construction is highly sensitive to certain small perturbations. Under specified perturbations, the modified family becomes decidable. This does not erase the original theorem. It shows that the physical robustness and scope of a construction matter when drawing conclusions about nature. The result, therefore, occupies a precise place in our investigation. Cosmic horizons showed that information can remain causally unavailable. Quantum mechanics altered the form of prediction. Chaos and complexity limited what finite observers can forecast. Spectral gap undecidability demonstrates that even with exact local rules and unlimited patience, some general questions about defined physical models admit no universal algorithmic solution. This does not prove that a theory of everything cannot be written. A fundamental theory could consist of concise laws, while some consequences of those laws remain undecidable. The theory might correctly define what happens, without offering an algorithm that settles every question we can formulate about its possible systems. That distinction cuts deeply into the meaning of understanding. If understanding means possessing the fundamental rules, undecidable consequences may be compatible with success. If it means having a method that answers every physical question generated by those rules, the spectral gap result supplies a rigorous counterexample within its scope. It also reveals why adding computational power cannot solve every limitation. Complexity asks how many resources an algorithm needs. Undecidability says no qualifying algorithm exists for all inputs. A computer running for longer may solve a difficult case. It cannot turn a non-existent universal decision procedure into an existing one. A contrast is an equation whose solution is expensive. If the required computation would take longer than the age of the universe, the answer remains algorithmically available even though no practical observer can obtain it. In an undecidable family, there is no guaranteed sequence of finite instructions that produces the correct decision for every input. The difference is between a road too long to travel and the absence of a road covering every destination. Both restrict an embedded scientist, but they do so for different reasons. Keeping them separate prevents the theorem from becoming sensational, while preserving what makes it profound. Exact rules do not ensure universal answerability. Could a more powerful non-algorithmic form of reasoning escape the barrier? That question remains controversial. Human insight can find proofs that one formal system lacks after adopting stronger assumptions. But the enlarged framework creates new limits. There is no demonstrated human ability to settle every undecidable case reliably. Still, our imagined final book could retreat again. It might admit that no algorithm derives every consequence while claiming to state the laws completely. Perhaps the universe follows those laws whether or not any computer can unfold them. The book would define reality without predicting it exhaustively. One obstacle remains that cannot be placed solely inside the mathematics. The reader of the book is part of the world described by the book. Its predictions can be read, remembered, resisted, or used to change what happens. The final test is not whether a machine can solve an abstract family of models. It is whether any physical predictor inside one universe can correctly infer every property of the system that contains it. Imagine a machine that predicts one simple choice you will make tomorrow. Before the appointed moment, it prints its forecast. You will press the red button. You read the message and decide to prove it wrong by pressing the blue button. Had the machine printed blue, you would have chosen red instead. The machine now faces a peculiar task. It is not predicting a distant planet that cannot read the result. Its forecast enters the system being forecast and changes what that system does. Whatever answer it announces creates the conditions for that answer to fail. This example does not prove that human choice escapes physical law. A sufficiently detailed account might describe the machine, the person, the message, and the response as one evolving physical process. The point is narrower. A device cannot always issue a correct, accessible prediction when the target is arranged to respond by contradicting it. Self-reference turns prediction into participation. A weather forecast can influence whether someone carries an umbrella, but it does not usually change the storm. A forecast about the complete behavior of an agent can become one of the causes shaping that behavior. The predictor must model not only the target's present state, but also what the target will do after learning the prediction. David Wolpert developed a mathematical framework for studying limits of this kind. Rather than assuming a particular computer or physical law, he described abstract inference devices. An inference device represents any physical system that performs tasks resembling observation, prediction, or recollection. It has a way of being configured and a way of producing an answer. The framework asks whether such a device can always answer yes or no questions about a universe that contains it. The questions may concern another system, a past event, a future event, or a property of the entire world. Because the device itself occupies part of that world, its setup and output belong to the same reality it is attempting to infer. Wolpert proved impossibility results that do not depend on whether the underlying universe follows quantum mechanics, classical mechanics, or some other detailed dynamics. In the relevant formal sense, no inference device inside a universe can correctly infer every possible binary-valued property of that universe. The logic resembles diagonal arguments in mathematics and computation. For any proposed universal predictor, one can define a question whose answer is arranged against the predictor's output. If the device answers yes, the target property corresponds to no. If it answers no, the target corresponds to yes. The contradiction is created by the demand for universality. This limit does not say that prediction is generally impossible. Devices successfully predict eclipses, chemical reactions, circuit behavior, and many other events. A weather model can improve even though it is not universal. Wolpert's result concerns the ambition to build one physical device capable of inferring every relevant property under every permitted configuration. The distinction is the same one that protected the spectral gap theorem from exaggeration. Failure of a universal method does not mean failure in every individual case. Science works by defining domains, testing models, and identifying conditions under which predictions are reliable. The impossibility appears when those limited successes are extended into total omniscience. That difference separates omniscience from ordinary scientific foresight. A model can remain excellent when it predicts a bounded set of variables under declared conditions. Trouble begins when its claim expands to every question, every configuration, and every response, including those defined specifically against its answer. Universality supplies the opening through which the contradiction inevitably enters. Wolpert's framework reaches beyond quantum uncertainty and chaos. Even in a classical universe with deterministic laws and no sensitive dependence on initial conditions, an embedded inference device can face these self-referential restrictions. Giving it more precise measurements or faster computation does not remove the diagonal construction. The limitation arises because the predictor and the predicted world belong to one system. The framework also defines a particularly powerful object, called a strong inference device, an analog of a universal computer for inference tasks. Wolpert showed that a universe cannot contain more than one device that strongly infers another in the required mutual sense. Complete, symmetric predictive mastery cannot be distributed among multiple embedded observers without running into incompatibility. The terminology is abstract, and its meaning should not be inflated. An inference device is not a theory of consciousness. The theorem does not state that every observer is confused about itself or that knowledge is an illusion. It formalizes limits on specified inference relationships. Its value lies in showing that some barriers follow from logic and embeddedness rather than from a defect in present technology. Return now to the final book. To describe everything, the book must include the physical state of its own pages or memory. It must include the process that produced each statement. It must include the reader's reaction and every change caused by that reaction. If the book predicts that a reader will choose red, and the reader uses that information to choose blue, the prediction becomes part of the event it failed to capture. Perhaps the book could hide certain predictions until after the event. Then it might preserve accuracy, but it would no longer provide the reader with complete advanced knowledge. Perhaps it could describe the reader as unable to resist. That may work in some cases, but not as a universal solution covering every possible target arranged to oppose its announced output. Perhaps the book could stand outside the universe and avoid inclusion in its own account. But if the universe means the total physical system, there is no scientifically accessible outside platform. Anything that interacts with the universe enough to observe and predict it becomes part of the enlarged system under consideration. This is the most intimate limit encountered so far. The cosmic horizon separated us from distant regions. Quantum mechanics constrained measurement and outcomes. Chaos amplified finite uncertainty. Undecidability restricted general algorithms. Self-reference shows why the observer cannot simply be removed from the description and granted a view from nowhere. Laplace's demon required exact knowledge of the complete present and enough power to calculate the future. But the demon itself has a present state. Its memory stores information. Its output affects other events. A complete prediction must contain the prediction and everything caused by it. The supposedly external calculator is folded back into the calculation. Again, the conclusion must remain exact. The result does not prove that reality lacks laws. It does not prove that no observer can understand itself in useful ways. It does not show that every prediction changes its target. It shows that universal, infallible inference by an embedded physical device encounters structural contradictions. The final book may still state fundamental laws. It may explain why countless phenomena occur and predict broad domains with astonishing success. What it cannot become is a perfectly accessible mirror containing every fact about the universe, itself, and every consequence of being consulted. The separate limits are now ready to converge. Each removed a different assumption from the Clockwork dream. Their combined force will answer the title, but only if we preserve one final distinction. Limits on an observer's knowledge are not automatically limits on reality's structure. We can now return to the library at the end of science. The final book still rests on its shelf, but the promise surrounding it has changed. To determine what it could truly contain, we must bring every limit together, without pretending that they are versions of the same argument. The first limit was causal access. Information reaches an observer through physical signals, and those signals travel no faster than light. Because the universe has a finite age and an evolving geometry, our observable region is bounded by horizons. The full cosmos may extend far beyond it. No telescope can collect a signal that has never arrived or will never arrive. This blocks a complete observational inventory from one location. It does not block universal laws. A gravitational law may apply beyond our horizon, even when the individual galaxies there remain unseen. The limitation concerns access to facts, not necessarily the geographical reach of a theory. The second limit concerned history. Science reconstructs the past through surviving records, but records can be diluted, scattered, hidden, or made compatible with several earlier scenarios. Inflation may explain observable features, while weakening traces of a preceding phase. Cosmic variance limits statistical certainty on the largest scales, because we observe only one cosmic realization. This blocks guaranteed recovery of every event. It does not make historical science unreliable. Evidence can strongly support one broad history while failing to determine every detail within it. The limitation concerns uniqueness and completeness, not the possibility of justified inference. The third limit changed prediction itself. Quantum mechanics provides exact probabilities for measurement outcomes, while resisting the classical assumption that every future result can be announced in advance. Interpretations differ about what lies beneath those probabilities, but experiments rule out important classes of simple local hidden variable explanations. This blocks Laplace's original form of certainty within the standard quantum framework. It does not block precision or lawfulness. A probability distribution can be tested and understood with extraordinary accuracy. The fourth limit came from chaos and computation. Deterministic equations may amplify tiny uncertainties until detailed forecasts separate. A compact law may generate consequences requiring more time or memory than any physical computer possesses. The universe need not be random for its embedded observers to face a practical horizon of prediction. This blocks the inference that determinism guarantees forecastability. It does not show that the equations are incomplete. The limitation concerns available information and resources. The fifth limit entered through undecidability. Gödel and Turing revealed that sufficiently expressive formal systems and general algorithms cannot settle every question generated within their scope. Spectral gap results then showed that a genuine property of constructed quantum many-body models can encode an undecidable problem. This blocks the belief that exact rules guarantee a universal decision method for all their consequences. It does not prove that every physical question is undecidable or that a final set of laws cannot be stated. The final limit was self-reference. A predictor inside the universe is itself a physical object. Its memory, output, and effects belong to the world it predicts. Wolpert's framework shows why no embedded inference device can correctly answer every possible binary question about that universe under the relevant conditions. This blocks universal, infallible prediction from within. It does not block bounded prediction, self-knowledge in ordinary domains, or the discovery of powerful laws. The force of the argument comes from keeping these layers separate. A causal horizon is not an uncertainty relation. Chaos is not undecidability. Computational cost is not missing evidence. Gödel's theorem is not a cosmological observation. Self-reference is not simply another name for quantum measurement. If one barrier disappeared, the others would remain. A future quantum gravity theory might revise our understanding of space-time without sending messages across every horizon. A quantum computer could accelerate important calculations without solving the halting problem. A deterministic interpretation of quantum mechanics would not grant infinite measurement precision or remove self-reference. The conclusion does not depend on one fragile mystery. We can therefore answer the strongest meaning of the title. If complete understanding means that one observer possesses every fact, reconstructs every event, and predicts every future outcome with certainty, the answer is no under the physical and logical conditions we have examined. Such knowledge would require access beyond causal boundaries, records that never disappear, unlimited precision and resources, universal algorithms where none exist, and a predictor exempt from inclusion in its own world. But the answer changes when understanding means discovering fundamental laws. Science has not proved that a unified and complete framework for all basic interactions is impossible. Such a framework may exist. It could reconcile quantum theory with gravity, reveal deeper principles, and explain why today's successful theories emerge at accessible scales. Even then, the framework would not become an inventory, a cosmic diary, or an oracle. It might define the lawful space of physical possibilities while leaving particular outcomes probabilistic, histories underdetermined, complex consequences computationally inaccessible, and some general questions undecidable. This is the climax's necessary complication. We have established limits on observers, measurements, algorithms, and formal descriptions. We have not established that reality itself is unfinished, irrational, or without a complete underlying structure. Epistemic limits, limits on knowledge, must not be confused with ontological limits, claims about what exists. The distinction prevents two opposite mistakes. One mistake declares that science will inevitably know everything because progress has always expanded knowledge. The other declares that because complete knowledge is impossible, science knows almost nothing. Both ignore the vast territory between ignorance and omniscience. The convergence changes what counts as failure. A theory does not fail because it cannot answer a question that no permitted observer could decide. A forecast does not fail because it reports a probability instead of certainty. An explanation does not fail because a level of organization requires concepts. Complete mastery was a standard built from assumptions of access, precision, computation, and detachment. Once those assumptions are tested, science appears less absolute, but more mature. It can map not only regularities in nature, but the boundaries governing attempts to know. Science occupies that territory. It discovers laws with stated domains, probabilities with measured confidence, histories supported by converging evidence, and limits demonstrated through theory and experiment. Its strength comes partly from refusing to call a model complete when its reach has not been established. The final book can now be understood more honestly. It may contain the deepest grammar available to any physical observer. It may unify what now appears separate and explain patterns across enormous ranges of scale. But it cannot serve as an accessible mirror of every fact, including every consequence of its own existence. One question remains before the verdict is complete. Are there plausible escape routes? Better technology, quantum gravity, non-algorithmic reasoning, or an imagined view from outside might seem capable of restoring the original dream. Each deserves a fair test, because a limit is meaningful only after its alternatives have been examined. The first escape route is better technology. History encourages confidence. Telescopes have turned faint points into galaxies. Detectors have revealed neutrinos and gravitational waves. Computers solve problems that once seemed unreachable. Future instruments will almost certainly expand the frontier again. But expansion is not elimination. A stronger telescope can gather weaker signals only when those signals arrive. It cannot observe beyond a causal horizon. A faster computer can explore larger models, but it cannot perform infinitely many operations, or implement a universal algorithm that mathematics proves cannot exist. Technology moves practical boundaries. It does not automatically erase structural ones. A second escape route is quantum gravity. Our present conclusions rely partly on theories known to be incomplete in extreme conditions. General relativity predicts singularities, where its description breaks down. Quantum field theory normally assumes a space-time background that gravity itself makes dynamical. A deeper framework may transform our understanding of space, time, information, and cosmic origins. Such a theory could reveal that some apparent limits were artifacts of current models. It might explain what replaces singularities, whether space-time is fundamental or emergent, and how information behaves in black holes. It could alter our account of the earliest universe and show that present ideas about horizons require revision. Yet quantum gravity would not automatically restore omniscience. A new law still needs evidence. An embedded observer still receives finite signals and uses finite resources. If the theory supports computation rich enough for undecidability, or permits self-referential inference tasks, familiar logical limits may reappear in new language. A deeper rulebook is not the same as a complete archive of its consequences. A third escape route proposes non-algorithmic understanding. Gödel showed that a formal system can fail to prove a statement that appears true from a stronger viewpoint. Some thinkers have argued that human mathematical insight may therefore exceed every algorithm. A recent proposal has extended this idea toward a non-algorithmic meta-theory of physics. This possibility remains speculative. Recognizing the limitation of one system does not demonstrate an ability to settle all statements beyond it. The stronger viewpoint relies on additional assumptions and faces questions of its own. No repeatable method has shown that human minds can correctly decide every problem inaccessible to algorithms. There is also an important difference between proof and execution. A formal system may be unable to prove a proposition about a process without preventing the process itself from occurring. Undecidability limits guaranteed methods of decision. It does not by itself prove that physical reality cannot evolve according to compact rules. Claims that incompleteness establishes a non-algorithmic universe, or proves that the universe cannot be simulated, go beyond current evidence. A fourth escape route imagines an observer outside the universe. From that external position, perhaps the whole cosmic history could be viewed at once, free from internal horizons and self-reference. The idea is easy to picture because humans routinely observe smaller systems from outside. But if the universe means the total physical system, an external scientific platform is unavailable by definition. Anything capable of sending us evidence would interact with our reality and become part of a larger system requiring description. An outside observer may have philosophical or theological meaning, but it cannot serve as a tested solution within present physics. The final escape route is not a new machine or theory. It is a better definition of understanding. Science rarely demands a list of every microscopic fact. It seeks compressed, testable explanations that reveal stable relationships, generate predictions, and state where they apply. No oceanographer must track every water molecule to understand a tide. No biologist must calculate every electron to explain natural selection. No cosmologist must observe beyond the particle horizon to test the expansion history inside it. Knowledge can be genuine without being exhaustive. This is not lowering the standard to protect science. It recognizes how explanation works. A useful theory separates relevant structure from irrelevant detail. It earns trust through successful tests, connection with other evidence, and openness to correction. Its limitations are part of its content. The escape routes reveal a pattern. Whenever a solution gains power, it inherits responsibilities. A wider theory must explain more evidence. A stronger computer remains a physical object. A higher formal system must justify assumptions. An external observer must somehow become observable. The dream repeatedly shifts its cost rather than removing it. Each rescue can deepen knowledge, but none supplies the detached, limitless standpoint that complete mastery demands. The remaining frontier is immense. We do not know the global size or topology of the universe. We do not possess a tested quantum theory of gravity. We do not fully understand the foundations of quantum measurement, the physical limits of computation, or the relationship between mathematical models and reality. These are active questions, not decorations placed around a predetermined answer. Future discoveries may move several boundaries. New observations could reveal primordial gravitational waves, or unexpected cosmic topology. New mathematics could classify systems now resistant to analysis. New physical principles could alter what counts as information or measurement. The responsible conclusion must remain open to those changes. Yet none of the escape routes currently restores Laplace's original dream in full. Better tools remain inside causal structure. Deeper theories remain distinct from exhaustive solutions. Non-algorithmic cognition lacks decisive evidence. An outside viewpoint lies beyond scientific access. What survives is not omniscience, but an increasingly connected network of reliable explanations. The final answer is therefore ready. It must distinguish what cannot be possessed, what may still be discovered, and what science never needed in order to understand. The book at the end of science may remain unfinished, not because every page is blank, but because reality can be intelligible without ever becoming completely contained. The library remains, but it no longer stands outside reality. Its shelves are made of matter. Its books occupy space. Its readers live within the history they are trying to understand. The final volume, if it is ever written, will be one more physical object inside the universe, not a view from beyond it. We can now answer the question in layers. Can one observer completely observe the universe? No. Every observer receives information through causal channels. The observable cosmos is not necessarily the whole cosmos, and accelerated expansion places some events permanently beyond contact. Better instruments can reveal more within the accessible region, but they cannot turn absence of a signal into direct evidence. Can one observer reconstruct every event that has occurred? Again, not in any guaranteed sense. The present contains records of the past, sometimes with extraordinary detail, but different histories can leave similar surviving traces. Information can be diluted, scattered, hidden by horizons, or rendered inaccessible. Scientific history can be strongly supported without becoming a perfect replay. Can one observer predict every future event? The classical promise fails on several fronts. Quantum theory may provide probabilities, rather than one certain outcome. Chaotic systems amplify finite uncertainty. Complex calculations can demand resources exceeding those available to any physical machine. Some general questions are undecidable, and a universal predictor becomes entangled with the world its predictions affect. Can science discover a complete set of fundamental laws? Here the answer remains open. No established theorem proves that a unified framework for all basic interactions is impossible. A future theory may reconcile quantum physics and gravity, reveal a deeper structure beneath space-time, and explain relationships that currently appear accidental. But even a successful final theory would not be every kind of understanding compressed into one equation. It would not automatically specify the universe's initial condition, list every event, calculate every complex consequence, or replace the higher-level explanations used by chemistry, biology, and other sciences. Complete foundations would not create complete possession. This is not a defeat. Science never became powerful by pretending to be omniscient. It became powerful by separating what is observed from what is inferred, what is measured from what is assumed, and what is established from what remains speculative. Its most reliable statements include their own conditions and limits. The discovery of a boundary can itself be a discovery about nature. The speed of light tells us how causation is structured. Quantum uncertainty tells us which physical quantities can be jointly sharpened. Chaos tells us how precision decays. Undecidability tells us that exact rules need not yield a universal answer procedure. Self-reference tells us why an observer cannot simply erase itself from the world it describes. These limits do not shrink the universe into meaninglessness. They make understanding more precise. We may never possess every fact, yet we can discover patterns spanning billions of light-years and fractions of a second. We can reconstruct cosmic history from ancient radiation, predict eclipses across centuries, and identify mathematical boundaries no machine can cross universally. The original dream treated knowledge as a finished map. Every region would be charted, every event labeled, and every road extended into the future. A better image is a growing network. Each reliable explanation connects observations, reveals mechanisms, and opens questions that were previously impossible to ask. Some of those questions may be answered by future generations. Others may remain beyond every observer, because no evidence can cross the required boundary. Still others may be meaningful only within a formal system that cannot settle them. Responsible science does not decide in advance which category contains an unsolved problem. It investigates until the difference becomes clear. So, can the universe ever be completely understood? If complete means exhaustively observed, perfectly reconstructed, and infallibly predicted by something inside it, the strongest answer is no. If complete means that its deepest fundamental laws can be discovered, the honest answer is that we do not yet know. Between those answers lies the real achievement. The universe can be intelligible without being exhaustible. Understanding does not require standing outside reality. It requires learning what can be inferred from within, how securely it can be known, and where the evidence ends. The final book may never close. That does not leave its pages empty. It leaves science what it has always possessed. Not the promise of absolute completion, but the ability to know more, correct itself, and approach reality with increasing precision. And that unfinished search may be our clearest understanding of all.